Hi everyone, in this video we are going to learn about memory safety in RAS. Now let's see what we are going to talk about. First we are going to talk about why is memory safety important. Then common memory issues in other languages. After that we will see how Rust is addressing memory safety concerns. And finally we are going to have a section where we understand variable lifetimes. So let's get started. Why memory safety is important? When a programming language is memory safe, it means that it protects developers from making mistakes that could lead to memory-related errors. These errors can be challenging to diagnose and fix, and they can also lead to security vulnerabilities if exploited by attackers. Memory safety is a crucial aspect of software development as it helps to prevent a wide range of bugs, vulnerabilities, and crashes in your programs. Memory safety ensures that our program can correctly access and manage memory resources without causing unexpected behavior or security issues. Now let's see what are the common memory issues in other programming languages. First, we have buffer overflow. This occurs when a program writes more data to a fixed size buffer than it can hold, causing the excess data to overwrite adjacent memory locations. Buffer overflows can lead to crashes, data corruption, or security vulnerabilities. Next, we have use after free. This happens when a program continues to use a pointer or reference to a memory after that memory has been freed or reallocated. Accessing freed memory can lead to crashes, unpredictable behavior, or even security exploits. And finally, we have data races. A data race occurs when two or more threads access the same memory location concurrently and at least one of them performs a write operation. Data races can lead to unpredictable behavior and hard to debug issues in your program. Now let's see how Rust is addressing memory safety concerns. First, here is our solution for buffer overflow. Rust enforces strict bounds checking on arrays and other collections, preventing programs from writing more data than the buffer can hold. This eliminates buffer overflow, ensuring that crashes, data corruption, and security vulnerabilities related to this issue are avoided. Next, we have our solution for use after free. Rust ownership system and borrowing rules ensure that memory is managed safely. Once a piece of memory is deallocated or moved, the compiler prevents further access to it. This prevents use after free issues, guaranteeing that your program doesn't encounter crashes, unpredictable behavior, or security exploits due to accessing freed memory. And finally, we have our solution for data races. Rust's approach to concurrency and its strict borrowing rules make it virtually impossible to introduce data races in your program. By enforcing that either a single mutable reference or multiple immutable references can access the data at given time, Rust ensures safe concurrent access to memory locations. This results in predictable behavior and eliminates hard to debug issues related to data races. If you remember, in our last video, when we were learning about borrowing and references, we said that we can have multiple immutable reference to a variable, but we cannot have more than one mutable reference, or we cannot have mutable reference and immutable reference to a variable at the same time. And we also solved this using some examples. Now, let's see how we can understand variable lifetimes. In Rust, variable lifetime refers to the duration for which a variable is valid and accessible within a program. Understanding variable lifetime is crucial for memory safety because it helps prevent common memory-related issues such as use after free and data races. Rust compiler, known as the borrow checker, enforces strict rules around variable lifetimes to ensure memory safety. Here's a simple explanation of how it works. When you create a variable, Rust allocates memory for it and variable becomes valid. As the program runs, the variable can be used within its scope, and Rust ensures that no other part of the code can modify or access the memory it occupies in an unsafe way. Once the variable goes out of scope, Rust automatically deallocates its memory, making it unavailable for further use. By managing variable lifetimes, Rust ensures that memory is accessed only when it's valid and prevents common issues like use after free. Additionally, Rust borrowing and ownership system enforces that only one mutable reference or multiple immutable references to a variable can exist at a time. This approach eliminates data races and further contributes to memory safety in Rust programs. I know this is a very theoretical part of this course, but we are going to use the ideologies that we talked here in our further lessons so that we can learn these ideologies by doing. So don't get worried about all this presentation. That's what we will be using in our later lessons. So thank you very much for this lesson, and I will see you on the next one.